I am very excited to continue our new seminar series with Salesforce AI Research. The goal of this seminar series is to bring together new conversations that promote research around AI for economics. We're interested in understanding the role that data, machine learning can play in developing new models for economics. And we're also interested in helping to respond to the global economic needs. So thanks to all of you for joining us. Just a reminder that we have a Slack channel for offline discussion, and there are links on the seminar page to the recordings of our earlier talks. Also, you can ask questions through the events using Zoom's Q&A function. I may interrupt Faye at any point during her talk if there are clarifications, and there'll also be plenty of time at the end for questions. So we're very happy today to host Fang from the School of Computer Science at Carnegie Mellon University. I know Faye well because before joining CMU, she was a postdoctoral fellow at the Center for Research for Computation and Society at Harvard University, where we had the chance to collaborate on problems related to market design for ride sharing. Earlier, Faye received her PhD from the University of Southern California in 2016. Her research lies in the field of artificial intelligence and multi-agent systems, focusing on integrating machine learning with game theory. Her research has won multiple awards, including from conferences such as IGCAI and IAAI, and with her dissertation recognized by both FRMS and also by USC. And Faye was recently named to the IEEE Intelligent Systems AI's 10 to Watch list for 2020. So I find her work to be fascinating for its combination of ML with game theory, as well as for its connections with societally important applications. So welcome, Faye, over to you. Please
Thank you so much. Yeah, thank you so much, David. And it's my great honor to be here and to give this seminar talk. As David mentioned, I was at Harvard a few years back as a postdoc working with David and also Professor Barbara Gross. And before that, I got my PhD from USC, was my PhD advisor being Professor Milan Tanfei. And now Milan also moved to Harvard. So I feel back home when I'm having this opportunity giving the talk to Harvard folks. So for my talk today, I want to talk about my research on kind of game theory and machine learning for multi-agent communication and coordination. But before getting there, let me talk a few words about my overall research. So today we are faced with many crucial challenges. We care about security, both in the physical world and in the cyber world. We rely on security agencies to protect ourselves and also critical infrastructure from potential attacks. However, there's always a lack of security resources. And we also care about environmental sustainability. We rely on rangers to fight against the poaching in the front line to stop the population drop of key species like tigers, and also to prevent other type of illegal activities like illegal logging or, and again, we don't have enough resources. And we also want to reduce hunger and increase poverty with the help of crowd-based platforms, but there's always a huge room for improvement in the operation of such platforms. If we look closer into these problems, then we may notice that they all involve multiple self-interested agents, like the defenders versus attackers, rangers versus poachers, or in the ride-sharing platforms, the platform versus users. And the questions that AI can help answer are how to allocate the limited resources and how to coordinate and communicate with the agents to achieve higher efficiency. And these are exactly what I want to answer in my research. And more specifically, I have been trying to developing game theory and machine learning techniques to help tackle these challenges. We have made some successful attempts. In my earlier work, we helped the US Coast Guard to design patrol routes for these for this kind of small patrol boats. Let me see if I can use a highlighter here. Oops, no. Yeah, to help the US Coast Guard to design patrol boats for such patrol routes for such patrol boats to protect the Staten Island ferry against the potential attacks. Since there are multiple ferries running and there are only 2 patrol boats, the Coast Guard used to choose one of the ferries and then ask the patrol boats to move along the ferry all along the way. And we modeled this problem as a defender-attacker game, and then designed a randomized patrol strategy for the defender. This strategy asks the patroller to take a route sampled from a probability distribution, which is carefully designed through mathematical programming with the goal to minimize attackers' maximum expected utility, because we assume that the attacker is perfectly rational and they would try to choose to attack the weakest point in the patrol. And on randomly chosen utility functions, we show that using this game theoretical approach, the potential risk level measured by the maximum attacker's expected utility is cut down by half. And as our work is brought to the real world in April 2013, it has resulted in a radical shift in the patrolling tactics of the US Coast Guard. And as shown in this video, the patrol boat is making a U-turn, which is a pattern that never happened in their previous patrols, actually. So in addition, we also worked with several wildlife conservation agencies to design patrol routes for the rangers. The rangers can remove snares like this, which are placed by the poachers to capture the wildlife. And different from the ferry domain, the poachers here are not necessarily expected utility maximizers, and it is important then to understand their behavioral model from data. And given data from past patrols and also satellite imagery, we have developed a series of machine learning models to predict the poaching threats, and designed a ranger-poacher game to compute the to predict the poaching threat, and also design a ranger-poacher game to plan the patrols for the rangers. And luckily, our work has been successfully deployed in multiple countries, including Uganda, China, and Malaysia. And actually, this photo is taken from a one-week trial patrol in northeastern China. They found 42 snares in just a week, which is much higher than what they typically find in a week. And I myself also went on patrols together with our partner organizations in different protected areas, including in Malaysia and in China. So these are some of the successful attempts that we have made in the past, and several of them are in collaboration with Professor Malentambe and his students. And today, I want to introduce more of my recent work on using machine learning and game theory for multi-agent communication and coordination. I would cover 3 topics. The first is the role of informants in the defender-attacker game. The second is the coordination through notification in the platform user setting. And the third one is coordination through correlated signals, with more focus on the first 2. So the reason why we care about informants in defender-attacker game is because of the concept of community engagement in anti-poaching. WWF has announced the 6 pillars towards zero poaching. In addition to the efficient use of rangers, they mentioned that it is very important to engage the community. And in fact, in the anti-poaching domain, because we are really in lack of patrol resources, sometimes the rangers would rely on the local community to provide information about the poachers and the poachers' plans of poaching. For example, they would recruit informants and ask them to provide tips about what they know of the poachers. And similar ideas of using informants has existed in other domains, like there are community watcher programs for urban security. And in this type of problems, we actually have 3 parties. We have the defender, for example, the rangers. We have the attacker, like the poachers. And we also have the informant, like the local community members. And after the attacker decides where to attack or where to place snares to poach the animals, the informant has a chance to observe or learn their attack plan and report that to the defender. The question here is, how should the rangers plan patrols with and without tips? And the challenge is that the informant's goal may not be always aligned with the defender. They may not always be helping the defender. In the anti-poaching case, sometimes the local community members would would welcome the poachers to place snares if they place snares close to their farms, because this can avoid the wildlife to ruin their farms. So in those cases, like their preference, at least for those regions, are not aligned with the defender. And when the informants who are strategic can choose what to tell to the defender. And therefore, we need to model the informant as a strategic agent when we determine how should the defender plan their patrols. So we model this as a defender-attacker-informant game. But let's start with first the defender and attacker game. So in the defender-attacker game, there's a set of end targets. The defender can choose a patrol strategy, which is a allocation of the R resources he has to the end targets. One resource can cover one target. And of course, a better strategy for the defender is to use a randomized allocation of the R resources to the end targets. The attacker can choose a target to attack. And the typical assumption is that the attacker can know the full strategy of the defender, and meaning what is the probability distribution of allocating the resources to targets, and then the attacker can choose which target to attack. And the utilities for the defender and attacker can be easily specified by 4 numbers for each target. So if the attacker chooses to attack target T, and the target has been covered by a resource from the defender, then the defender gets a reward, and the attacker gets a penalty. Otherwise, if it is not covered, the defender gets a penalty, the attacker gets a reward. However, when here comes the informant, we need to reason about the informant's preferences and their actions. We assume that the informant has a type selected from a set big theta, and there is a prior distribution over the types, which is known to all the players in this game. And the informant can choose to send a message to the defender. And the utility for the informant is dependent on their types. So if the attacker attacks target T and the informant is of type theta, then the utility for the informant is UT covered if the defender covered that target, and UT uncovered, represented by U here, of theta, if the target is not covered by the defender. And because of the existence of the informant, now the defender not only needs to choose a patrol strategy, but if in fact the defender needs to choose a defense plan. This defense plan has 3 components. The first component is this set of messages. Basically, the defender announces the set of messages and asks the informant to report one of the messages in this set. And the defender also needs to determine a routine patrol strategy. That is, when the defender does not receive any messages from the informant, what strategy it would use. Again, it is a randomized allocation of the R resources to the end targets. And in addition to that, it needs to provide an X, which is a mapping from the messages to a patrol strategy. So for each possible message, it provides a patrol strategy it is going to use. And then in the actual execution of this, in the actual execution of the game, what happens is that the defender first commits to a defense plan, which is announced to the attacker and the informant. And then the attacker determines to choose a target to attack. The informant, after observing the target that attacker attacks, can decide which message to report to the defender. The informant may not always observe the target attacked, it only observes it with some probability. And then the defender would act according to the defense plan. That is, if it doesn't receive any message, then it executes X0. If it indeed receives some message, then it uses a patrol strategy in the mapping of X. And of course, there may exist many possible defense plans, because the defender can design any kind of set of possible messages. And we call it a direct defense plan if the defender, the set of messages the defender design is simply the set of targets times the Cartesian product of the set of targets and the set of types. That means the defender asks the informant to directly report what target he observed and what is his own type. And you may wonder that, okay, the informant may not be willing to tell his true target, his true type, and the actual target he observed. So we call a directed defense plan to be truthful if reporting the actual target and the informant's true type is the informant's best strategy. And
you have a question?
Yes.
You have a question, Faye, from somebody in the audience. They ask whether you think that poachers will adjust to these new methods of detecting them. Have we seen any instance yet of this adjustment happening?
Yeah, very good question. So in practice, we do see that there are informant reporting to the rangers, and the poachers may not necessarily know the informant. Sometimes they're aware of the existence of the informants, but they don't know exactly who in this community is the informant. So because of that, they may still kind of unintentionally release their attack plans. Sometimes, like what we heard from the site managers, is that sometimes the poacher will talk about their plans when they go to restaurants or in the karaoke type of places. And then the people there would know their plans. Sometimes they will report to the ranger. So that's like what we learned from like the domain experts. Yeah, so now as we can see here, like the direct defense plan is like a simplest form of defense plan. And of course, we would like to find out a truthful defense plan. And in fact, what we notice is that for any possible defense plan, there exists a truthful direct defense plan such that all the players can observe the same utility for any target and any type. It is actually the same as the revelation principle in mechanism design, and the idea of proving it is the same. That is, if I have an original defense plan where there is a set of messages the defender has designed, and the informant has come up with their own strategy of reporting which message to the defender, then we can build a new defense plan based on this strategy in the original defense plan. In this new defense plan, we kind of lie on behalf of the informants, and so that the new defense plan collects the true type and the target information from the informant and execute their original strategy in the original defense plan. And by doing so, this overall new defense plan becomes direct and truthful. And now the next question we want to ask is, how many messages do we actually need in this type of game? Of course, we have this upper bound. We have already known that we can design a direct defense plan, which requires n times omega messages. So the omega is the number of types the informant have, n is the number of targets we have in this whole problem. However, can we have less messages? Can we use less messages? The answer is yes. We were able to show that there exists a defense plan with only n+1 messages that can achieve the optimal defense utility. So again, n is the number of targets. The idea is that this n messages can be classified as n messages, and this n+1 messages can be classified as n messages and an additional message. So this message 1 to n is kind of like the message for the pro-defender informants. So intuitively, you can view it as if the informant is aligned with the defender, then it would report the true target, which sends this message from 1 to n. And if the informant is not aligned with the defender, then the informant would rather not to tell anything useful to the defender. So in this case, the informant can report the n+1's message to the defender. And for a specific target T, the informant would directly report message T if he is defender aligned, meaning the utility for him is higher if the defender covers target T comparing to when the defender does not cover target T. And the informant would report message n+1. If it is better for the informant if the defender do not cover that target. So that's kind of the intuition of this theorem. And building upon this theorem, we can also show that we can actually compute the optimal defense plan in polynomial time. The idea is that we're going to solve a linear program for each target. In this linear program, we are going to use constraints to ensure that the attacker's best strategy is to attack a specific target T. And also, the informant's best strategy is to report message T if the informant is defender aligned on that target T. And the informant's best strategy is to report the message n+1 if the informant is attacker aligned on that target T. And this LP is just enough to find out the optimal defense plan. And remember that previously we also talked about the directed defense plan. We can actually also compute a optimal directed defense plan using the similar ideas. Like we are building multiple LPs, one LP for each target. And in each LP, we ensure that the attacker's best response is to attack target T and that the informant's best strategy is to report truthfully. So the idea is similar. And the reason why we propose this solution is because it has less constraints and variables. And in the experiments, we see that when we randomly sample the utility functions for the informants, we see that the more likely that the informant is defender aligned, the higher the defender can get, the higher the defender utility the defender can get. And of course, when the informant is more likely to be attacker aligned, the attacker can get a higher utility. And in addition to this internal incentives of the informants, the defender or the rangers can also try to provide some external reward to the informants so that to incentivize them to report truthfully or to report messages that are favorable for the defender. And indeed, we notice that when we reward the informants with some like very little external additional reward, it can already lead to a huge utility gain for the defender. So this is kind of some of the results we get, and we can see what we learn from this problem is that the informant can play an important role in this defender-attacker interaction. And recently, we are working on extending this work to multiple informants case, and we're trying to see. We have our preliminary results show that again we can find out a good defense plan with using a linear programming method. So we are looking forward to see how we can apply this method to different domains, because currently we're still having this model like somewhat in theory. Although we talked to our domain experts in wildlife conservation, we haven't get a chance to really discuss with them on how to deploy it in practice. The second topic I would like to cover today is coordination through notification and platform user settings. And here, the problem is actually motivated by the, motivated by the volunteer-based food rescue platform. We know that food waste and food insecurity coexist in many parts of the world. In fact, data shows that we waste up to 40% of our food globally, which is more than 1.3 billion tons annually, which is a huge amount of food waste. On the other hand, 1 in 8 people go hungry every day. So how can we help? One way to help is to rescue the good food. And that's exactly why this kind of food rescue platforms exist. What they do is that they contact grocery stores, restaurants that has unsaleable food, but which are still in good condition, that are like healthy and eatable, and trying to send this food to the community in need of food in a timely fashion, so that those food don't go wasted. And how it works is that they have this smartphone app, and they would post this rescue request on the smartphone app. Each rescue request says, I would like to have the food delivered from picked up from restaurant A and sent to community B before 10 a.m. or some kind of other times. And after they posted this rescue request, a volunteer can registered on this smartphone app can claim a rescue. And after they claim the rescue, they can go to pick up the food from the donor and then deliver it to the recipient, and that will succeed. And these photos are actually taken from my own experience. This is when the cafe in the CMU has leftover muffins. And then we send the muffin to a local organization, which is helping the single moms with low income. So this whole project is in collaboration with a food rescue platform here in Pittsburgh called 412 Food Rescue. So the challenge of running this kind of food rescue platform is that because it is a fully volunteer-based platform, there's a lot of uncertainty about whether or not the rescue will be claimed and can be completed by the volunteers. They have come up with their own ways to dealing with this problem. First of all, they would send notifications to volunteers when the rescue comes in. And this kind of notification can be viewed as like a one-to-many communication. The platform wants to communicate with many users or volunteers on this platform at once. However, the issue with this is that the volunteer may experience the notification fatigue. They may get a lot of notifications and they may end up ignoring the notification completely. Another way they do is they have the human dispatcher jump in, and they would call a specific volunteer they're familiar with, or even text a specific volunteer and asking specifically whether are you willing to help with this rescue. And this is more like a one-to-one communication, but as you can expect, there is a very limited number of human dispatchers. The human dispatchers will be overstretched when they're dealing with this job. They have to monitor all the rescues. So how can AI help? First of all, AI can try to provide a predictive model of the rescue claims status, and it can help determine which rescues need the special attention from the human dispatcher, so that it can reduce the workload of the human dispatchers. In addition, AI can provide a data-driven optimization of the intervention and notification schemes, so that we can avoid excessive notifications, and which can help retain the volunteers. We can help determine who to send the notification to and what is the schedule of sending the notifications. We've worked on both tasks. First, we looked at how to provide a predictive model for the rescue claim status. Using the operational data set of 412 Food Rescue from March 2018 to May 2019, we are trying to predict which rescues will be claimed by volunteers. And to do so, we first try to look at the data. We noticed that the percentage of unclaimed rescues varies a lot in different regions. And this is a Pittsburgh map, and the regions represent different zip codes. We can see that in some of the regions, the percentage of unclaimed rescues is much higher than others. And we talked to the domain experts, and also based on our own experience, we come up with a set of features that can be used for the predictive model. This including timing-related features, weather-related features, and location-related features. And based on these features, we can build a model that predicts whether a rescue will be claimed by the volunteers. So the label here means whether or not a rescue will be claimed by any volunteer. As you can see, we have more than 3,000 claimed rescues and around 750 unclaimed rescues. So it is actually an imbalanced data set, but we used sampling techniques to get a more balanced data. And we split the data into the training data and the test data. We're trying to use the past to predict the future. So we use the data from May 2018 to December 2018 to be the training data, and the data from January 2019 to May 2019 to be the test data. We use a stacking model that is among the training data. We split it to be two parts: data set A and data set B. We use dataset A to train multiple basic models using random forest, using Gaussian processes with different kernels and different parameters. And we actually use the 5 different Gaussian process-based models and 1 random forest-based model. And after we training these base models, we use the second part of the dataset, the dataset B, to determine how to aggregate the results from these base models to make a final prediction. So we build a neural network that takes as input the output of the base models and generates a final prediction. And the stacking model was able to predict the rescue claim status pretty well. And it can achieve an AUC of 0.81. And comparing to the other baseline models, like simply using random forest, simply using gradient boosting, or simply using Gaussian process, the stacking model can lead to a higher precision and a higher AUC. Here, I put a star here in the precision because it is not exactly perfect. It is like, because of the rounding, it is close to perfect. And we are particularly interested in the precision here because, in fact, in this domain, a lower precision leads to a higher cost comparing to a lower recall, because a perfect precision means that there's no false positives. All rescues that are predicted to be claimed are indeed claimed. And if the precision is actually low, then it means there are many rescues predicted to be claimed but are in fact not claimed. This is particularly concerning because a low precision can lead to the failure of a rescue, which is definitely undesirable. And in contrast, if the recall is slightly lower, it's okay because it only means we bring a little bit more claims to the human dispatcher's attention than necessary. So the cost is affordable. Because of all these factors, we believe that the stacking model actually is the best model to use in this setting. And this is our ROC curve. And again, we see that the stacking model has a better ROC curve with leading to a higher AUC. But the predictive model is not the only thing that we care about. We also want to optimize the intervention and notification scheme. The current practice is that immediately when the rescue is published, it would send the first wave notification immediately to all of the volunteers within 8 miles of the pickup location. They will wait for 15 minutes, and if the rescue is not yet claimed, it would send the second wave notification to all the volunteers. And if it is close to the deadline, like if it is already like 60 minutes to the deadline, then the human dispatcher would jump in and try to contact individual volunteers themselves. And this 60 minutes is really very rough estimation because when we talk to them, they're saying that, oh, we don't really have a rule of thumb for when to contact the individual volunteers. We just based on our own experience. And when we look into the data, we notice that around 664 volunteers will get the first wave notification. However, only 44.6% of the rescues are claimed by the volunteers receiving this first wave notification. That means there is room for improvement. So what do we want to do? We want to improve this intervention and notification scheme by changing the parameters in the current INS, the scheme. we want to determine the best value of this X, Y, and Z's so that we can reduce the notification and human intervention while ensuring the same claim rate. And we can convert this problem into an optimization problem. We want to minimize this objective function, which comes with 3 parts. The Vy is the expected number of volunteers receiving the first wave notification. The Qxyz is the number of volunteers receiving the second wave notification. And this Sxyz is the number of rescues requiring the human intervention. And this lambda is a coefficient kind of measuring how much we care about the human intervention and how much we care about the notifications. Subjected to the constraint that this Pxyz, meaning the claim rate using the current notification scheme, is larger or equal to the current threshold, which is determined by the current default scheme. And of course, we have some other basic constraints on the value of xyz. Here we simply assume that the x and y and z should be selected from a certain interval. So how can we solve this optimization problem? There are still 2 challenges. The first is, how can we estimate the value of Vy, Qxyz, and Sxyz and Pxyz given a combination of xyz's? We have to make a number of assumptions. We assume that the rescue and the volunteer distribution remain the same in the past and in the future. And then we estimate these quantities based on the historical rescues. So for each rescue, we calculate the counterfactual claim time under a intervention scheme with a number of assumptions. For example, we assume that upon receiving a notification, a volunteer would take the same amount of time to respond. And we also assume that when the human dispatcher jump in and contact the individual volunteers, whether or not they can succeed is not affected by the INS used. So, and there are a number of other assumptions. With these assumptions, then we can look at our historical data and historical rescues, and we can calculate for each rescue what is the time that it would claim by the volunteers, and use that to estimate this V and Q and S and P. Even with this, there's still a challenge because we're considering the XYZs in a certain interval. And in theory, there are many, many combinations of XYZs. And for each combination, we need to compute this counterfactual claim time and then estimate the cost, the objective values. And that's too costly. And can we avoid enumerating all the possible INSs? We decided to estimate a lower bound of the objective value with a INS when only a subset of parameters are specified. So for example, if at some point we specified the value of y and z, but we haven't specified the value of x, then we can estimate the lower bound of the objective function by using the extreme values of x and when estimating those quantities. By doing so, we can use the lower bound to prioritize and prune different INSs through branch and bound. For example, like we start with none of the parameters specified, and then we expand this root node by specifying the value of z for different values. And then we compute the lower bound for each of these branches, and we pick the branch with the lowest lower bound and expand it further by specifying the value of y. And then we calculate the lower bound again, and again pick the one with the lowest lower bound and expand further by specifying the value of x. And here, once we have all the XYZs specified, we can use our counterfactual estimation to calculate the objective value. And let's say for this node, we found the objective value is 2,500, and then the lower bound of this node is actually 2,600. Then what we know is that there's no need to branch this node further. We don't need to consider any possible axis with y equals 4.5 and z equals 45. So by doing so, we can speed up the whole process of finding a good intervention scheme. So we optimize the values on, we optimize the XYZ values on data from May 2018 to December 2018 and test on the data from January 2019 to May 2019. And with different values of lambdas, we come up with different optimal values of XYZs. So here, the yellow line is for X, red line is for Y, and the blue line is for Z. So these are the optimal values of them. And when we talk to the 412 food rescue folks, we need to recommend a new notification scheme to them. And to do so, we try to map the values of the expected number of interventions and the expected number of notifications with different lambda values, and then recommend the schemes by checking the Pareto frontier. So specifically, we notice that the current intervention scheme is here in the represented by this green star, and then ideally we want to recommend an intervention scheme that is in this yellow region, and we find out that the only one that we have is in this yellow region is this point A. And in addition to those, there are alternative choices, which, for example, for this recommended NISB, represented by this orange diamond, it has a significant lower number of human intervention required, but it would need to send out 2% more notifications to the volunteers. So eventually, we recommended these two intervention schemes to our collaborators, and then they decided to deploy the first one because it seems to be strictly better than the current one since January 2020. We're still working with them to try to extract the data from them and try to analyze what actual impact this new intervention scheme has led to in practice. But after this, we continued thinking about the problem. Can we do better than simply changing these parameters of the default intervention scheme? The idea is that we want to send out the first wave notifications to volunteers that are really more likely to claim the rescues. And this reminds us of the recommender system. So what we want to do here is that given a specific rescue, we want to provide a list of K volunteers for which we should send notification to. It's somewhat similar to the recommender systems, where here the users are the rescue trips and the items are the volunteers. In the typical recommender system, we recommend items to users. And in this setting, we try to recommend volunteers to the rescue trips. And to do so, we analyzed the distribution of donor and recipient organizations. And based on this analysis, we divide the Pittsburgh area into 16 regions. And as we can see, some of the regions has a lot more donor organizations and recipient organizations. And based on this division of regions, we construct features. For each rescue and volunteer combination, we extract the following features: the number of volunteers who completed rescues in the donors region, the number of volunteers completed rescues in the recipient region, and of course the total number, the number of volunteers, the volunteers' total number of completed rescues, and also the time and the distance. Using these features, we construct a neural network-based model and try to predict whether a rescue will be claimed by a specific volunteer. So here, the positive label means it is claimed, negative label means it is not claimed. Notice that we have more than 6,000 rescues and more than 9,000 volunteers. When constructing this data set, we need to construct a data point for each rescue volunteer combination. So it's a huge data set. It is also highly imbalanced. So we have to use sampling techniques to make it more balanced. And again, we're trying to use the past to predict the future. And how it works in building this model is that the rescue volunteer information, for each rescue and volunteer combination, we extract the features, and then we send to the neural network, which would predict the probability that the volunteer J will claim the rescue I. And once we build this model using the training data, now we can recommend the volunteer following this procedure. So given a rescue, we need to enumerate all the possible volunteers and use our learned model to predict the probability that each of the volunteer would claim that rescue. And based on these results, we rank them from top to bottom according to these probabilities. And then we pick the top K volunteers and send push notifications to them. To evaluate our model, we use the metric of hit rate at top K. That is the percentage of rescues that are claimed by volunteers in the top K. And we choose K to be 964 because the default INS would send 964 notifications to the volunteers on average. And what we found here is that using this neural network-based recommender systems, it can lead to a much higher hit ratio at top K comparing to the current practice. So this is a significant improvement, but there's a caveat. The caveat is that when we use this machine learning-based recommendation, it would discover some frequent volunteers and keep sending notifications to them. And if we look at the distribution of the push notifications, we can see that there is some volunteers here that receives more than 1,000 notifications for this 1,300 rescues. This is clearly undesirable. So how can we deal with this challenge? We decided to use online planning together with this machine learning model that we have learned. Rather than we greedily taking the top K volunteers, we would enforce some constraints such that each volunteer would receive at most ELK notifications every day. And to achieve this, then for every time we receive a rescue, we need to determine who to send the notification to by planning with a projected set of future rescues. So let's say I'm currently at 10 a.m., I received a rescue. And I know that I have already sent some notifications to some of the volunteers in my volunteer pool. I need to determine which volunteers I should send notifications now. Then I need to envision what kind of rescues I would receive in the future, because I may need to save some of the volunteers for the future rescues. And to do so, we use like the historical dates, say yesterday. I know that yesterday after 10 a.m., I have these 3 rescues. So I projected those rescues to today. And now I can plan my rescue by solving an optimization problem. I try to determine whether to send notification to a rescue I to volunteer J, given the output of the machine learning model, which would indicate that the probability that the volunteer J would claim rescue I. And also given the constraint that how many notifications volunteer J can still receive for the rest of the day. So the optimization problem is rather straightforward. I want to maximize the sum of the probabilities for the current rescue and also for the projected future rescues, subject to the constraint that I cannot send more than K notifications for each rescue. And for each volunteer, I cannot exceed their daily budget of notifications. So by solving this optimization problem, we noticed that we can avoid this over-concentration, even with a budget of 5. So we send at most 5 notifications for each volunteer every day. And as we can see here, now the distribution with using this online planning is similar to the default notification scheme. And in fact, the hit ratio at K is now 0.6, which is still much higher than the current practice, although it's not as good as the when we don't have any constraint on the L, on the number of notifications one can get. So this is what we learned from this problem. When we have this platform user interaction, how can we leverage the machine learning techniques to communicate and coordinate with the volunteers? And in the interest of time, I'm not going to go through into details for the third topic. I just want to mention what we wanted to do in this coordination with through correlated signals. So people are probably familiar with correlated equilibrium, which is a solution concept proposed in 1970s, where the assumption is that there is a correlation device that can send private signals to the players. And then the signals are sampled from a joint distribution over the actions of players. And it actually represents the recommended player behavior. And the correlation device sending the private signals to the players, and the players would, the players receiving the signal would determine what action to take. And the goal here is that we want to design the correlation device such that it recommends the behavior of the players, and the players would happily accept it. The player would be willing to follow the recommended behavior by the correlation device without any enforcement. And there's a classical game of chicken dare problem. And in this problem, the Nash equilibrium can lead to a total utility of 9, but a correlated equilibrium can lead to a higher utility. And this shows that when we have this signal sending to the players, we can potentially achieve a higher social welfare. And what we are trying to do here is to see how can we find out a way to learn to learn what kind of signals to send, and to learn how the players should behave upon receiving the signals. So the first attempt we did here is that we try to design the probability distributions so that through learning, so that we can find out a way that the agent can coordinate with each other. The technical challenge is that we need to find out a good way to represent the joint probability distribution, especially when it is a complex setting like with continuous signals. And here we decided to use a copular to represent the joint probability distribution, and then trying to learn the copular and find out the best joint probability distribution. So we parameterize this copular with a neural network, and then trying to learn the parameters in this neural network to ensure that the players have the incentive to follow the recommended action. That's what we wanted to do. But at this point, we haven't successfully completed the whole workflow yet, because we find out that just designing that copular that is learnable is already challenging enough. So what we actually did is that we focus on the Archimedean copulars, which is a way to represent the joint probability distribution. And it's a simpler class of copulars with a simple parameterization. And the Archimedean copulars is specified by a generator, which can be represented, which can be kind of parameterized by a single scalar theta. And what we do is that we constructed this Archimedean copular network that learns the generator as a convex combination of negative exponentials. And therefore, the only thing we need to learn is just the parameters in each of the exponential functions. And by doing so, we can kind of combine this AC net with the existing deep learning techniques, and we can use gradient descent to learn the parameters in this AC net. So we were able to show that this AC net is able to represent some of the example joint probability distributions, including some of the real world data set. So going back to what we actually want to do, given that now we have this AC net that can flexibly represent different forms of joint probability distribution, we want to find a way to learn the AC net such that it is closer to a correlated equilibrium. So that is kind of what we want to do with this AC network. So that's it for today. I covered 3 ways of communication and coordination in multi-agent interactions. And we are looking at the future. I'm envisioning using more, developing more machine learning and game theory techniques for communication and coordination, and also for addressing different societal challenges. So with that, I'm happy to take questions.
All right, thank you, Faye. That was awesome. We do have some questions, so why don't we Why don't we dive in? First of all, there was a question back in the food rescue setting. I know you were focused on the supply side of the problem and on how'd you get volunteers to go and actually get the food that's available. But there was a question that came in about who has access to the food rescue, and is there any way to ensure that the food itself goes to the people with the greatest need? Is that a problem that you've been looking at as well?
Yeah, that's a great point. I know that Ariel Procaccia actually has some work on dealing with this problem, like eliciting the preferences of the recipients in this food rescue setting. And here we focus on the other aspect of the problem, which is like the coordination and communication with the volunteers.
Right. Okay. Yeah. Thank you. So there was an advert there for Ariel Procaccia's work, so you should all check that out.
Yeah.
I think maybe where we'll go next. Amy Greenwald has been asking some great questions about evaluation. So I'm going to start with the first part of her question. She asks, she'd like to hear more about how policies are evaluated when deployed. In the Coast Guard example, you told us that the policy where the boat made a U-turn was new, but you didn't say it was better. How would we know whether the policies are an improvement over the status quo?
Yeah, very good question. So we did the evaluation both in the in-lab setting and also through like collecting feedback from the experts. So as we can see in the in-lab setting, we compare the expected utility within the game model that we develop. Of course, you may say that, okay, the model itself is probably missing some of the practical aspects. And that's why we have to talk to the folks in the Coast Guard and to see what kind of evaluation that they think would be appropriate. So they had this kind of red team attack type of thing. So like they have this mock attackers and to try to determine how should they attack if they are the attackers. And the feedback we get from them is that it becomes harder to plan the attack because of this randomized patrol strategy and because of the increased randomness and also the higher probability of protecting the targets when the target is more valuable. And in addition to this kind of mock attackers, they also collect the feedback from the people who are running the patrol boats, and they told us that there is a increased level of randomness and unpredictability. So that actually they feel like their work becomes more like unpredictable and it's like less routine. And they also collected feedback from the marinas who are typically like working on that water area, and they commented that there is an apparent increase in the number of in the Coast Guard patrols, while the actual number of patrol boats and the number of patrol hours is actually the same.
I see. Have you ever seen any opportunity to be able to kind of run almost a randomized deployment trial where you take some locations that are somehow similar to each other, and in some of the locations you deploy your new policy, and in other locations you leave the status quo policy, and hopefully you can match these locations up well enough so you can try to get some estimate of the causal effects of the policy change. Have you seen any opportunities like that in your work?
Yeah, so in the Coast Guard setting, definitely very hard. We didn't get any chance to do that. So in the wildlife conservation setting, it is actually, there's a higher chance to do so, but it's still a very challenging thing. So what we have done before is that we tried to have the rangers patrolling the area, like using our AI-based techniques, and then to see how many snares they found, how many times they encounter the potential poachers, and compare that number with what they typically get in that region without using our tools. So we can see that there is a higher number. And also in collaboration with Milan, previously we had some controlled experiments in Uganda where we pick more than 20 regions and then classify them as highly high threat regions and low threat regions based on our machine learning model, and then send the rangers to different regions and compare the number of poaching signs they found in these regions. And again, we show that the high threat regions have a lot more poaching signs found comparing to the low threat regions that are predicted by the machine learning model.
Yeah, thank you. Kind of a related question. I think I'll try to tie together two of the questions we got from the audience here. They're both kind of asking about utility modeling assumptions. So Amy again points out that, of course, in a Stackelberg modeling context, you do have a leader-follower view, and therefore you are allowing that the behavior of the follower will change, depending on the policy changing of the defender. Of course, at the same time, the efficacy of that model, its ability to capture behavior, will depend on the utilities that you ascribe to the followers, the attackers in your model. And kind of a related question from a Harvard College student is, how do you formulate the utilities for the players in your games?
Very good question. And it has been a hard question from the very beginning when we try to use this game theory models for these practical challenges. I remember when I was a PhD, when we are still working on game theory models for output security, we have already been receiving questions like this. And in those settings, what they end up doing is that they try to ask the domain experts to estimate the importance level of different targets under different scenarios. And for the fairy protection problem that I talked about, what we provide is essentially the algorithm, and clearly the utility functions are actually specified by the users. And based on our conversation with them, what we learned is that they determine the utility values based on how many passengers are there on each of the ferries at different time slots, and also the location of the ferry. Like if the ferry is close to the terminal, then a successful attack would not only impact the passengers on the ferry, but also the people who are waiting on the terminals. So they would have a higher utility when it is close to the terminals. So these are the factors that we have learned when we talked to the domain experts. And I myself don't really have access to this kind of utility functions because I don't have security clearance, and this is sensitive information clearly. And I think in general, it is a challenging problem of determining what is the appropriate utility functions. Recently, we also tried to tackle this problem from the inverse game theory perspective. That is, if we know the historical attacks, then can we try to estimate the attacker's utility function, assuming that the attackers are somewhat rational when they choose which targets to attack. And we designed some learning-based approach to estimate the utility functions. And I think this only works when you have enough data, of course. And for the domains with very limited data, it is still currently based on the domain experts' knowledge to determine the utility values.
Thank you. Yeah, I mean, one of the things that's very clear about your work, Faye, is that you really are engaging in a very deep and serious way with the stakeholders and the domain experts. And actually, one of the questions from the audience goes there. So we have a question that says, I love that this work is all tied to practical applications, but still makes serious contributions to theory. Could you talk a bit about how working with domain experts changes your modeling choices and your analysis goals? And whether also, do you find it challenging to convey the theoretical parts of your work back to them?
Yeah, that's great questions. So for about working with domain experts, in the wildlife conservation domain, initially we worked on the model in the lab, saying that, okay, we divide the whole area into a 1 kilometer by 1 kilometer grid. And when we design patrol routes, we ask the rangers to go from grid A to the neighboring grid. And then we send this suggested patrol route to them. And then they come back to us saying that this is completely nonsense. Because in practice, the protected area that they were working on is a very hilly region. So it is very hard for them to directly move from point A to point B following the straight line that we provide. So we end up coming back to the lab and end up taking into account the terrain and completely remodel the patrol planning part. And we end up building a virtual street map for the conservation area by connecting the reach lines, the stream lines, those passes that are easy to follow, and then design patrol routes on this virtual street map. And in the food rescue case, initially we came up with all kinds of potential problems that we can use AI for. And then after the conversations with them, and after we ourselves working as a volunteer, we realized that those initial thoughts are very silly. So we end up pinning down to these questions that the stakeholders believe are important to them. And we think that AI technique can indeed be used to tackle them. And the other question is it challenging to convey these results to the domain experts? Yes, indeed. We have made a lot of attempts to do this. First of all, what we see is that initially, especially when the first versions of the models, typically you need to use some interpretable models and convey the results to them. For example, in the wildlife conservation domain, the initial versions of the machine learning models are mostly decision tree based, because we can visualize the decision tree and explain to them, like if this location is close to the village and it is close to the road, then there's a higher chance of poaching, because this is something that they can understand. And after that kind of first iterations of collaboration, we build trust among us. And now it becomes easier for us to build more advanced models. And even if they cannot fully understand the techniques, now they feel like you're doing something that is really for them. You're not trying to fool them or anything like that. So this is another way that we find extremely useful. We have come up with we have to provide all kinds of data analysis that are intuitive to them. So for example, in the food rescue, in addition to the work that I introduced in this talk, we have to do a lot of other kinds of analysis. For example, we help them to analyze what is the average gap time for the volunteers between their consecutive rescues, and all kinds of data that statistics or quantities that are of interest to them. And by doing so, they again feel like what we're doing are useful and are satisfying their needs, and they're more willing to go in deeper with us and to collaborate on some harder problems.
Yeah, that's great. So you find ways to be useful back to them.
Yeah.
We're almost out of time, but I do just want to quickly just get a quick reaction to the first question that we got, which is a very interesting question. Essentially, the question asks whether you see opportunities for reinforcement learning in your work, of your 412 rescue work with supervised learning, what are the roles for multi-agent reinforcement learning? Are you excited about that as a direction?
Yeah, very good question. So actually, in recent years, I have been worked a lot in multi-agent reinforcement learning. So in the anti-poaching domain, we are trying to use multi-agent reinforcement learning to design an adaptive patrol strategy. That is, when the rangers see the footprints left by the poachers, how should they respond? And this kind of problem is much harder. It involves sequential decision making. So we use multi-agent reinforcement learning to find the strategies. And then in the food rescue domain, I also think that it is possible to use reinforcement learning-based technique to find out a better notification scheme. And for the coordination through correlated signals, we also tried to see, like in the multi-agent reinforcement learning perspective, how can we design the learning algorithm so that the agent can learn to make use of the signals and coordinate with each other.
Okay, we are at time. Thank you, Faye, for such a wonderful talk. And we're so glad that so many people were able to join us today. Looking ahead, next seminar that we'll have will be on March 9th, and it will feature Tori Grappel, Research Group Lead at DeepMind and Chair of Machine Learning at UCL. And I think we'll hear about reinforcement learning then. So thank you again, Faye, and wishing everybody a great rest of your day.
Thank you.
Thanks, everybody. Bye-bye.
Bye-bye.